Let's dive right into this explainer and absolutely demystify the core concepts of electric circuits, getting you completely exam ready for your grade 10 physical science assessments. I know circuits can sometimes feel like this invisible, frustrating puzzle, but once you can actually visualize what's happening inside those wires, I promise you, everything just clicks into place. We're going to lock down your definitions, build an unbreakable mental model, and master the exact calculation skills you need.
So, have you ever wondered how trillions of tiny particles instantly figure out where to go the exact second you flip a switch? It feels like magic, right? Well, it's not magic, it's physics. By the end of this explainer, you are going to understand exactly how those electrons navigate a branching network, almost as if they have a mind of their own.
Okay, here's our rapid-fire roadmap for today. We'll meet voltage, current, and resistance, tackle Ohm's law and conductors, look at the two views of the circuit, figure out splitting the current, and wrap up with a series and parallel summary.
Let's jump into Section 1, meeting the core trio of voltage, current, and resistance.
Now, according to the strict Grade 10 exam guidelines, terminal potential difference, which we usually just call voltage, across the ends of a conductor is defined as the energy transferred per unit electric charge flowing through it. That is represented by the formula V equals W over Q. Voltage is measured in volts. And listen, you absolutely have to know this definition word for word for your tests.
But let's strip that down and simplify it. Think of voltage as the essential, fundamental energy push that gets used up just to get those electrons through the circuit. Without voltage, there is literally zero motivation for the charges to move. It's the raw energy provided by your battery or power supply that drives the entire journey of the electron.
Moving on to current. The official definition for current strength is the rate of flow of charge. It's measured in amperes, which is the exact same thing as coulombs per second. The formula we use here is I equals Q over delta T. A quick pro tip, make sure you heavily emphasize the phrase rate of flow in your written answers, because that is exactly the keyword your markers are hunting for.
In the story of our circuit, current represents the traveling electrons themselves, just moving along the conductor. When they encounter parallel branches, they don't just stop in their tracks, they split apart. And as they split, they make a crucial choice. They will always prefer the path of least resistance. The easier the pathway, the more electrons will rush right down it.
And finally, we have resistance. The guideline officially defines resistance as the ratio of the potential difference across a resistor to the current in the resistor. This definition gives us the very famous relationship R equals V over I, which is measured in ohms, where 1 ohm is equal to 1 volt per ampere.
Visually, let's give resistance a more microscopic description. I want you to imagine it as physical friction or heat. It occurs when electrons are literally knocking into each other and into the particles of the metal conductor, transferring their kinetic energy. This massive slowdown happens when the pathway is really long, when it's just too narrow, or when there is simply something directly in the way, like a light bulb. Because of all this friction, voltage, that energy push we talked about a minute ago, gets used up just trying to force the electrons past these obstacles.
Moving right along to Section 2, Ohm's law and conductors.
Ohm's law tells us that the potential difference across a conductor is directly proportional to the current in the conductor, provided the temperature remains constant. Definitely keep that constant temperature condition in your head. It is a classic, totally ruthless trap in multiple choice questions. Essentially, this means if you increase the voltage push, the current flow is going to increase right along with it, as long as the resistance doesn't heat up and change the rules.
As highlighted beautifully in the Ciavula textbook, we can clearly see the difference between materials here. First, we have ohmic conductors, things like your standard circuit resistors and nichrome wire, which maintain a completely constant resistance, even when the voltage is varied. They obey Ohm's law perfectly, which gives us a nice straight line graph. On the flip side, we have non-ohmic conductors. These do not obey Ohm's law. Their resistance actually changes, usually because they start getting hot, resulting in a curved graph instead.
All right, Section 3, two views of the circuit.
So there is the circuit which the current sees, which is the full, complex electric circuit with all of its parallel and series branching components. To the current, the whole thing is basically a giant maze to navigate. But then, there is the circuit which the voltage sees. Voltage essentially strips it down and sees a simplified, equivalent circuit where everything is just in series. Viewing it from the voltage's perspective tells us exactly how the energy will be proportionally split and used up across the entire system. Honestly, understanding how to switch between both of these views is your ultimate superpower for complex exam questions.
That brings us to Section 4, splitting the current. Let's actually apply this to a classic grade 10 past paper question where, let's say, a 2 ohm and a 4 ohm resistor are set up in parallel. When calculating exactly how current splits here, you've got two approaches. The regular method takes 3 steps. First, because we know potential difference is always the same across parallel branches, you determine the voltage across that entire parallel section. Second, you pinpoint the specific resistance of the individual branch you're interested in. And third, you just apply Ohm's law, I equals V over R, using that branch's specific voltage and resistance to calculate the exact current flowing through that specific path.
Alternatively, we have the ratio method, which is an incredible time saver once you master it. You start by determining the ratio of resistance between the branches, like our 2 ohm and 4 ohm resistors. Then, and this is the absolute secret to this trick, you invert the ratio. Why invert it? Well, because as we established earlier, current vastly prefers the path of least resistance. The branch with a much smaller resistance is going to get the much larger share of the current. Finally, you just divide your total current proportionally based on that inverted ratio. The vast majority of those electrons are going to safely rush down the easiest possible path.
And finally, Section 5, the series and parallel summary. I highly recommend taking a quick screenshot of this ultimate summary matrix because it perfectly captures exactly how resistance, voltage, and current behave depending on whether they are in a series or parallel setup. Let's run through it. For resistance, as resistors are added in series, the total resistance increases, using the formula Rs equals R1 plus R2. But in parallel, as resistors are added, the effective resistance actually decreases, using the formula 1 over Rp equals 1 over R1 plus 1 over R2. For voltage, in a series circuit, voltage splits and gets used up across the individual components. In parallel, voltage absolutely does not split, it is equal in all branches. And finally, current. In series, current does not split at all. It's equal to the total current everywhere. But in parallel, the current splits into the different branches. It doesn't get used up, remember, it simply prefers the path of least resistance.
I'm going to leave you with this final, slightly tricky thought to test your understanding of everything we've just covered. If current absolutely loves the easiest path, does the hardest, most resistive parallel path get completely 100% ignored by the electrons? Keep visualizing that electron journey. Keep practicing your ratio calculations, and you're going to completely master this circuits exam.